Hello everyone and welcome to the multiple choice session of S block elements. We will be dividing the entire sessions into two parts. Okay, the first part, which will contain around 25 questions, will restrict ourselves to alkali metals. After that, the next 25 questions we will restrict ourselves to alkaline earth metals. Okay, so as we start with this particular session, I would like to show you one particular important slide, and that is about the weightages. If you observe the particular exams that you are looking forward to attend, NEET, there are going to be two questions from this particular chapter. Okay, JEE mains you can expect around 3 questions. BITSAT again, total weightage is given as 2. Okay, so whenever you are looking forward for the chapters, observe the chapters with highest weightages and give more importance to that. That's all I want to say. Okay, now, what are the concepts which are very, very important where we have to focus a lot? First one is how are the periodic properties, how are these particular properties are going to vary in periodic table. Okay, second one is what are the properties of alkali metals and alkaline earth metals, followed by the preparations. Okay, if you see the difficulty score, it is going to be 3 out of 5. So you can say moderate type of questions you can expect from this particular chapter. So starting with the first question, and that is the magnitude of which of the following property of alkali metal increases with increase in the atomic number. Now, they are specifying themselves over here with respect to the alkali metals, right? So alkali metals, what do we have? The alkali metals that we have are lithium, sodium, potassium, rubidium, and cesium. So as we go down this particular group, what happens is atomic number goes on increasing. Let's observe electronegativity. Now, electronegativity is nothing more than the ability of an atom to drag the shared pair of electron towards itself. Now, that particular electronegativity actually decreases as we go from the top to the bottom because as we go from the top to the bottom, the atomic size increases. As the size increases, the distance from the nucleus to the outermost electron goes on decreasing. Due to that particular fact, we can say that electronegativity actually decreases, it's not increasing. Second one exactly is the actually ionic radius. Now, it is the size of an atom goes on increasing. If the size of an atom goes on increasing with increase in atomic number, right? So as atomic number is increasing, what we know is it is directly influencing the size. So therefore, the size of an atom, that is going to increase. If the size of an parent atom is increasing, of course it has direct relation with its ionic size. So therefore, we can say that as atomic size is going to increase, of course, the size of ion, that is going to increase. Okay, so therefore, our answer over here lies with actually with B. Let's observe the second one. First, ionization energy. Now, first ionization energy, that means we are trying to remove the outermost electron, right? So, as we go down, what is going to happen? The size of an atom goes on increasing. As the size of an atom goes on increasing, the amount of energy that you require in order to remove the outermost electron goes on actually decreasing, because the distance from the nucleus to the outermost shell, that is going to increase. Secondly, the screening effect also comes into existence over here. So therefore, as we go down, the first ionization energy actually decreases. And of course, the melting point has been considered. Now, melting point. What is going to happen with the melting point? As we go down the group, sizes between the atoms are going to increase. The distance between the atom is going to increase. As the distance between the atom is increasing, bond length is increasing. Okay, as bond length increases, over here the boiling point and the melting point that have a direct effect. That is, the melting point decreases going down this particular group. Okay, so our answer is strictly only and only with respect to the ionic radius. Okay, so this one is the first answer. coming to the question number 2, and that is, which is the most basic in character? Now, speaking about a base in this particular regard is nothing more than a substance which has a capacity to donate OH minus ion. Okay, so a bases are nothing more than a substance which are going to donate OH minus ion with respect to the S block element section. So it's been concerned. Now here, please observe that we have right from lithium to rubidium, all these particular metals. Of course, we have OHs with all of them, that means all of them are basic. Now here, as we see, lithium, next one we have sodium, next one we have potassium, followed by rubidium. Right. So as we go down this particular group, can we say that the size of atom is going to increase? Okay, so size of an atom over here is increasing. Now as size of atom increases, that means the distance between the element and the OH group, of course, is going to increase. Right. So therefore, as the distance from the metal and the OH group increases, it can easily liberate this particular group. Okay, greater the distance between the metal and the hydroxyl group, easier for that particular compound in order to give away OH group. That means this particular process of donating OH minus ion becomes easier. So in this particular case, what will happen is, as we travel from the top to bottom, okay, the basic strength goes on increasing. That means we have the rubidium hydroxide, which is more basic in nature. So therefore, our answer over here goes with A, that is rubidium hydroxide. Okay, so this was for the question number 3 now. That is, among these, which one has the density greater than water? Okay, now remember, over here from the lithium to sodium to potassium, rubidium, cesium. Okay, so what is going to happen now is, as we travel down this particular group, the density goes on increasing. Of course, lithium is the lightest metal, so you cannot expect it to show you a denser property. So therefore, as we travel down, simple concept, the density goes on increasing. So therefore, here the density increases. Okay, so density is increasing down in a particular group. So therefore, in this particular case, we do not have cesium, we restrict ourselves to rubidium. So therefore, rubidium has a higher density than water. So therefore, the answer is C. Coming towards the next section, and the question number 4 is RbO2, that is rubidium superoxide actually. Okay, so rubidium superoxide is A, peroxide and paramagnetic, B, peroxide and diamagnetic, C, peroxide and paramagnetic, D, superoxide and diamagnetic. Now, here, if you observe the formula, Rb and we have O2. Okay, so a substance having 2 oxygens like this. Okay, these are usually nothing more than super oxides. Okay, so if it is like Rb2O2, okay, in that particular case it becomes as peroxides. Now, when we are observing this condition, okay, Rb plus O2 with a minus charge. This is the particular ions which are present in the superoxide. Here, we need to understand about this. There is one unpaired electron. So whenever there is one unpaired electron that is present, it has a direct effect on the magnetism of a particular substance. If a particular substance is getting affected in the magnetic field, we call it as a paramagnetic. Okay, if it is not showing any response, we call it as a diamagnetic. So now here, due to this one unpaired electron, which has a particular spin, it can be plus half, it can be minus half. So it is going to show some effect under the presence of an external magnetic field, and therefore we call it as the paramagnetic in its nature. Of course, it is superoxide, and it is going to show us paramagnetic characters. Okay, so answer over here is superoxide and paramagnetic in its nature. Okay, so let's observe the next one. The word alkali is used for the alkali metal that indicates A. Ash of plant, B. Metallic nature, C. Silver luster, and D. Active metals. Now, this one goes with a history. Okay, now observe here that alkali, okay, this particular term is actually obtained from Arabic language. Okay, so in Arabic language, this terminology has been derived from al-Qali, which actually means ash. Okay, now the Arabs found out sodium and potassium from the ash of plants, due to which this particular term as alkali has been derived. So therefore, our answer over here is the ash of the plants. Okay, so alkali is nothing more than the ash of plants. You need to remember that. So, coming towards the question number 6. The ease of adsorption of hydrated alkali metal ion on an ion exchange resin follows the order. So, we have all different elements which have been placed over here. Okay, so first we'll understand what is this particular thing that we have got it over here as adsorption. So, in order to understand that, let's say that this is nothing more than a surface of a sphere, okay, of the exchange resin, ion exchange resin. Okay, it has an ion in it. Now, let's say this, on the other hand, is nothing more than your entire liquid area, okay, wherein you have different type of ions which have to be exchanged. Now, here, whatever the ions that you have in this particular area, what will happen is, the smaller the size of an ion, okay, the smaller the size of an ion, the better it gets hydrated. That means it has a higher hydration enthalpy. Okay, it has a higher hydration enthalpy. Now, as the size of an atom or an ion goes on increasing, okay, then it has a direct effect on its hydration enthalpy. That is, greater the size, hydration enthalpy goes on decreasing. So, as the size of an atom or an ion goes on increasing, hydration enthalpy goes on decreasing. And now, as the hydration enthalpy decreases, the process of adsorption also decreases then. Okay, now what is adsorption? Adsorption is nothing more than a process wherein the ions will come and they just stick to the surface of a particular substance, and that is called as adsorption. So adsorption is going to decrease with increase in the size of an ion. So what we have to remember here is the process, the adsorption is going to decrease with increase in size of ions. So, if we take this particular statement into consideration, that means the highest one is actually lithium. Lithium ion is going to get absorbed more better in particular quantity, okay, in better in efficiency. So, after that comes is the sodium. After sodium comes is potassium, then rubidium, then cesium. Okay, so this is the fashion which is going to be followed. So therefore, we have here exactly opposite one. If we see here, B, that is lithium is going to be greater than sodium, sodium is greater than potassium, potassium is greater than rubidium. So therefore, we have the answer B in this particular case. Okay, so this is for the ease of adsorption. Coming towards the question number 7. The stability of the following alkali metal chlorides follows the order. Now, first we shall observe over here, that is, they are speaking with respect to alkali metal chloride. Okay, fine. Now, whenever an alkali metal chloride or any substance that is formed, okay, so let us say that this is going to represent as alkali metal halide. Whenever a substance is formed, its stability directly depends upon the one important aspect, and that is the enthalpy of formation. Okay, now enthalpy of formation, we give it as, or we represent it as delta HF. You are going to study this entirely in detail in a chapter called as thermodynamics. Okay, now it all depends upon enthalpy of formation. For your understanding, let us say now that when a substance is formed, a small amount of energy is liberated, and that small amount of energy that is liberated, we give it as negative. If it is liberating, we give it as negative, exothermic reaction. If it is absorbing, we give it as positive, endothermic reactions. Okay, more the amount of energy that is released, more stable this particular compound is going to be formed. Simple concept as that. Okay, more amount of energy that is going to get released, more stable your compound is going to be formed. Now, if we observe the first one, that is lithium chloride. Okay, so here delta HF value what we have is minus 408 kilojoules per mole. Okay, as we travel down, that is with respect to NaCl, what we see is delta HF value is going to be minus 412 kilojoules per mole. Similarly, if we see of cesium chloride, it is going to be delta HF is equal to minus 433 kilojoules per mole. And finally, of course, what we have is potassium chloride, and that is going to be delta HF is equal to minus 436 kilojoules per mole approximately. So, more the number or more the amount of energy that is going to be released, more stable is our compound. So, taking that statement into consideration, can we say that the most stable compound is KCl, the least stable compound is going to be our LiCl. Okay, so two extreme cases: least stable, lithium chloride; extremely stable is potassium chloride. Okay, so taking that into consideration, we can say that this is highly stable. Anywhere else? No. So least stable is this, and therefore my answer is A in this case. Alright? Proceeding further with the question number 8. Reaction of hypo with iodine. Okay. Hypo is nothing more than Na2S2O3. So sodium thiosulfate. Okay, so this is sodium thiosulfate, which is again nothing more than what we call it as hypo. Now, we are taking a look over here with the reaction with iodine, right? So, whenever a reaction with iodine is concerned, so first thing that it gives us is 2 NaI plus Na2 SO4. So, in order to balance it, let us say that we have 2 in this case plus I. So now, in order to balance it, so the number of iodine that we have used is 2 into 2, 4, 4 plus 2, that is going to be 6. So therefore, we are going to take over here 3I2. Okay, so what it is giving me over here is nothing more than this is sodium tetrahydrite. Okay, so the reaction of hypo with iodine actually gives us sodium tetrahydrite. Now here, when we speak about sodium sulfide, that is nothing more than Na2S. Okay, sodium sulfide is Na2SO3. Sodium sulfate is Na2SO4. Of course, sodium tetrahydrite, as what we have here, is Na2S4O6. Okay, so it gives us sodium tetrahydrite. It's advisable for you people to take down all of these. Okay, write it down, keep it safe, and revise it. Coming to question number 9. Among these, which does not decompose on heating? Okay, so whenever we have these particular carbonates, usually like magnesium carbonate, okay, as we start to heat it, it forms MgO plus carbon dioxide. That means it is releasing carbon dioxide. Okay, we are going to take a look into one more question in a similar fashion, but only the type of question represented is going to change. That we are going to have it in short time. Okay, so according to this particular reaction, at least I have already represented over here, magnesium carbonate decomposes on heating. Okay, now let's observe about the lithium carbonate. So lithium carbonate upon heating is Li2O. Because of this, it's going to form lithium oxide plus carbon dioxide is going to get ejected out. Okay, of course, the same goes true with calcium hydrogen carbonate, Ca. Okay, now as we heat it, upon heating, it is going to give calcium carbonate plus what remains is H2O plus carbon dioxide. Okay, but what does not decompose here is sodium carbonate. Sodium carbonate does not decompose on heating. It's just not one, rather we also have potassium carbonate. Even this particular potassium carbonate does not decompose on heating. This is what we have to remember. Okay, so this goes true with respect to the sodium. Next question, and that is question number 10. The bed of amphoteric hydroxide is. Now, first thing we need to understand is what is exactly an amphoteric. Okay, so amphoteric hydroxide here. So amphoteric hydroxides or amphoteric oxides, also you can say. Okay, so amphoteric ones are nothing more than these particular substances which have a capacity in order to react with both of them. Both of them, in a sense, it can react with an acid, it can also react with a base. Okay, now, whenever we have metals, the metals such as we have zinc, copper, aluminium, tin, etc. These particular metals, okay, their oxides as well as their hydroxides, they have a capacity in order to exhibit amphoteric nature. Okay, of course they are going to exhibit amphoteric nature, but we need to observe here the pair of it. Now, when we observe aluminum hydroxide and its oxide, of course they are amphoteric, but not lithium hydroxide. Lithium hydroxide is a base which is not an amphoteric in nature. So therefore, lithium hydroxide is not correct pair to go on with this. Beryllium hydroxide, on the other hand, actually even that thing is amphoteric in nature. We have already discussed this in the properties of beryllium hydroxides. Okay, so beryllium hydroxide is an amphoteric in nature, but again, magnesium hydroxide, no. Now here, beryllium and barium hydroxide, again not a correct option. So zinc and beryllium hydroxide, this one is actually the correct answer. So remember this particular case, this particular scenario. Okay, so the pair of amphoteric hydroxides are beryllium hydroxide and zinc hydroxide. See, the question number 11, it's similar to that of question number 10. Okay, here again we are indirectly asking about the amphoteric nature. Okay, options are same, everything is same. So here the pairs are not matching. That is, this is amphoteric while this is not amphoteric in nature. This is amphoteric and again this is not amphoteric in nature. Beryllium hydroxide again amphoteric, but barium hydroxide is not. Okay, so boron hydroxide is not an amphoteric in nature. So here is where again answer is D for this particular case. Okay, so let's observe the question number 12. So question number 12, based on the lattice energy and other consideration, which one of the following alkali metal chloride is expected to have the highest melting point? Now this is the knowledge based type of question, wherein you should know that the highest melting point of alkali metal chloride, and that is sodium chloride. Okay, so sodium chloride is actually the metal chloride which is having a highest melting point. So this is a knowledge based type of question. Okay, so let's observe the next one. Question number 13. Which of the following is incorrect? Okay, first one, all carbonates are soluble in water. No. All carbonates. Now carbonates, if I take into consideration of calcium carbonate, again it is not going to be soluble in water. So therefore this is of course incorrect. Let's observe the next one. Carbonates of sodium, potassium and ammonia are insoluble in water. Again it is wrong. Here if we take into consideration of sodium carbonate or potassium carbonate, okay, of course ammonia carbonate also you can take ammonium carbonate there. So these are actually soluble in water, but they have given over here as insoluble, again which is actually wrong statement. Okay, so carbonate of calcium, strontium and barium are insoluble in water. Now here is where we need to be very careful. Now here calcium salt, that is calcium carbonate, okay, CaCO3, this is insoluble in water. Perfect, that is correct. But when we observe with respect to strontium and barium, okay, now these two things are actually soluble in water, and therefore I cannot go with again option C. Okay, so therefore option C, option B and option A are not correct. So therefore I would say as all of these. Correct? So all of these are incorrect statements. Coming to the question number 14. The element of group 1A provides color to the flame of Bunsen burner. That means whenever you are taking the salt from the group 1A and you are inserting it to the flame. Okay, so it is going to give colors. We have already seen about the different types of color that is going to be exhibited, right? So now the thing is, why this particular color is coming into existence is because whenever you have any of the alkali metals, okay, now this particular alkali metal atoms, when we observe these particular atoms, as you observe them carefully, okay, whenever they have the electrons, the outermost electrons, these outermost electrons have a very, very low ionization enthalpy, due to which when you provide energy to these particular atoms in the form of flame, okay, the energy is being taken up, it's been absorbed by these electrons, as a result of which these electrons get excited to a higher level. Okay, as it gets excited to the higher level, okay, it stays there for some time and then again it gets de-excited. The moment that it gets de-excited, it releases good amount of energy in the form of radiations. And those are the radiations which you can actually see as colors, color of flame. Okay, so therefore, it's actually the low ionization potential. So it is because of low ionization potential, not because of melting point, not because of softness, not because of presence of one electron in outermost shell. All these alkali metals have one electron in their outermost shell, but that's not a correct option. That's not a satisfactory explanation why, as these particular elements are going to exhibit colors to flame. Okay, let's observe the next one. Question number 15. The sequence of ionic mobility in the aqueous solution is. Now, observe here, they are speaking about in aqueous solution, ionic mobility. Ionic mobility, in a sense, how better your ions. Let's consider this particular thing as ion here. This is the second ion over here. The third ions. I am taking into consideration of different sizes of ions just for our explanation, in order to make the explanation much more easier. Okay, so ionic mobility is nothing more than how better the ion can pass, can move through a given solvent or solution. Okay, so in this particular case, ionic mobility is nothing more than the movement of ion through the given solvent, but the given solvent over here is an aqueous medium. So when it is an aqueous medium, what is going to happen is, smaller the size of ion, okay, the better hydrated it is going to be. So smaller ions are going to be highly hydrated. That means it is going to get reacted with water ions. It is going to react with water molecules. It is going to attach themselves with water molecules. When it is going to get attached to water molecules, then the mobility becomes difficult. Now, as we go down the particular group, from lithium to sodium to potassium to rubidium, the size of ions goes on increasing, right? As the size of ion goes on increasing, what happens here is that as these sizes increases, here hydration is going to decrease. As hydration decreases, these ions can move much more easily compared to those of the smaller ions, because smaller ions are getting hydrated much more better manner. As due to the hydration, the mobility, the movement of these ions is going to be reduced. As that happens, so can we say that it's actually the rubidium which is going to have the highest mobility, and the least mobility is going to be governed by that particular lithium. So therefore, we have the answer over here as A. Right? So 15th answer is A. Coming towards the question number 16. The solubility of alkali metal carbonate. Okay. Now, alkali metal carbonates. Let's take over here. Lithium carbonate followed by sodium carbonate followed by potassium carbonate, and then we have rubidium carbonate, cesium carbonate. Okay, let's have these. So now what they have given: increases at first and then decreases. Okay, does not show any regular variation. All right, increases as we go down the group, decreases as we go down the group. Okay, so what happens when we come down the group? Of course, the carbonate section remains common in all the cases. What changes is the size of these particular atoms. Okay, so as we come down the group, here the atomic size, the size of atom, it is going to increase. As the size of atom is increasing, the solubility has a direct effect, and that is the solubility is going to increase. So therefore, the solubility actually increases going down a particular group. Okay, so the option is C. The strongest reducing agent in the alkali metal is, we have already seen about this. Okay, so over here for the 17th, the strongest reducing agent is lithium. Okay, for 17th, lithium is strongest. Now here, least, the downest one. Okay, the lowest one is sodium. The highest one is lithium, the lowest one is sodium. Okay, remember that. So answer over here is A. Okay, so let's observe the next question. Okay, so I had already given you a hint a few questions back, saying that you will be having the same kind of question with respect to the decomposition. And here is it. Which of the following does not give CO2 on heating? Okay, so we have already seen how this particular calcium carbonate is going to decompose, giving rise. Okay, sodium carbonate, lead carbonate, lithium carbonate. Again, it is going to be sodium carbonate, which does not give you carbon dioxide on heating. Next question, and that is question number 19. Fire of lithium, sodium and potassium can be extinguished by. That is, how can you put off the fire of lithium, sodium and potassium? Now, use of water against the alkali metals is going to enhance the reaction. Okay, it is going to react violently with them. So you cannot use water. Using nitrogen is going to form nitrites. Lithium nitrite, sodium nitrite and potassium nitrites. So therefore, we cannot again use the nitrogen in this case. However, the use of carbon dioxide, okay, so when we use carbon dioxide, it does not help. It does not help in burning. Secondly, it would rather form carbonates. So it will not support burning and it converts these particular alkalis into their respective carbonates, and therefore option C is the correct answer. Okay, so let's observe the next question. Consider the following observation for the hydrated alkali ions. Okay, so what we have is X is equal to lithium hydrate, correct? And times Y is equal to what we have is potassium hydrate again. Z is equal to cesium hydrate. n times. Okay, so now they are asking for these particular hydrated alkali ions. Okay, what will be our observation? That is, x is greater than y is greater than z, or z is greater than y is greater than x, or all the three of them are same, or z is greater than x is greater than y. Now here, how to understand these particular questions? It all goes with the hydration energy. Okay, so enthalpy of hydration. So as I already said, this enthalpy of hydration, it goes with the smaller ions. Smaller the ions, better it gets hydrated. So therefore, applying this particular concept, so we need to find the smaller ion. If you get the smaller ion, you get the answer. So, smaller ion, which among of these is smaller? If you observe carefully, it's actually the lithium is smaller. After lithium, it is the potassium which is smaller. Final comes is the cesium. Okay, so lithium, which is forming lithium hydrate, okay, stands first because of its higher hydration enthalpy. Next one is your potassium hydrate, which stands second, and finally is the cesium. So, taking this particular thing into consideration, I would say that x should be greater than y should be greater than z. This is our answer. So, if you take a look, it is the first one. Correct? Okay, coming towards the next one, and that is the fusion mixture. Now, this is a knowledge-based question. You have to remember this. Okay, it is going to be a knowledge-based question, as which composition we call it as the fusion mixture. It is a mixture of sodium and potassium. Okay, now here, sodium and potassium, we have two things, one here and one here. Okay, so carbonates of sodium and carbonate of potassium, this mixture, we call it as the fusion mixture. So therefore, here is sulfate, so we cannot use this. So our answer is Na2CO3 and K2CO3. So this particular mixture, Na2CO3 and K2CO3. We call this particular mixture as fusion mixture. Okay, so that is for the fusion mixture. Let's observe the next one. Question number 22. Which of the following alkali metal is expected to melt if the room temperature rises to 30 degrees Celsius? Now, there are certain metals such as mercury, okay, we have cesium, and we have gallium. These particular type of metals usually exist in the form of the liquid state if the temperature rises more than 30 degrees Celsius. So therefore, it's the answer cesium. Okay, so cesium exists in form of the liquid state if the temperature is greater than 30. The microcosmic salts. First thing is we need to understand as what exactly is this microcosmic salt. Microcosmic salts are those particular salts which are derived from the human urine, okay, in a crystallized form. Now that particular thing is called as the microcosmic salt. Now that is a combination of sodium, ammonia, and what we have is the phosphate. Okay, so sodium ammonium phosphate is the microcosmic salt. Okay, so question number 23, option is C. To question number 24, and that is the most stable compounders. Okay, fine. Let's observe here, as they have given us lithium fluoride, lithium chloride, lithium bromide, and finally lithium iodine. So as we go down this particular group, the size of halogen is increasing. As we have lithium on one side, what changes is the halogen. So as the size of halogen goes on increasing, okay, so as the time that we come at this particular stage, what will happen is lithium positive charge, iodine negative charge. Ionic character has built up so much, and the distance between the two ions is also greater now because of the increased size of ion, that is of iodine. So therefore, this particular bond can be easily broken, okay, due to which lithium iodide is the least stable one. Exactly opposite, that is, as we go on the top, over here, more covalent type of nature is been seen. Covalent type of nature wherein the electrons are shared rather than the electron being getting transferred. So therefore, in this particular case, in this particular scenario, we can find a covalent nature which is much more responsible for making this particular compound stable, and therefore our answer is A. Okay, so more stable compound is lithium fluoride. Finally, coming to the question number 25, and that is, among these, which is incorrect statement? So fluorine is more electronegative than chlorine. Okay. Next one is nitrogen has greater IE1, that is first ionization enthalpy, than oxygen. Lithium is amphoteric in nature. Chlorine is an oxidizing agent. Now, here we have a direct hint. As I already said about the lithium, lithium cannot be amphoteric in its nature. And so therefore, lithium is amphoteric in nature. This particular statement is not correct. So therefore, we cannot expect this particular answer there. Of course, fluorine is more electronegative than chlorine. Perfectly correct answer if we go through a periodic table. Okay, variations of the electronegativities holds good. Nitrogen, of course, has a greater first ionization enthalpy than oxygen. Chlorine actually is an oxidizing agent with respect to electrons. So therefore, what remains is the lithium, that is amphoteric in nature. Okay, so here we would like to stop with respect to the with respect to the alkali metals. In the next video, we will take a look into alkaline earth metals. To take care.